Okay, let us start. Good evening, friends. Today we will discuss about industrial robotics and its application. Myself, Professor G.MOORTHY, Mechanical Engineering Department at Velammal Institute of Technology, Chennai. Next. Our outline of the presentations comprises Introduction to Robotics, what is robotics, international Indian scenarios in robotics, robotic subsystems, how robots are classified, topics of interest in robot design, overall view of robotic softwares, that is commercial softwares available to design the robots, how students can contribute in robotics, finally conclusions. This is our outline of our presentation. Coming to introduction to robotics. Here we are doing we have taken a lot of examples how the robots are applied to the requirements. We are going to see about space exploration robots, earth-based robots, small biologically inspired robots, industrial robots, how it is functioning in automotive sectors, finally next generation robots. We are going to discuss. So coming to space exploration robots, you had seen that you had come across the name called Curiosity land roving rover, which is used to rove the Mars planet to find any organics which is present there in the Mars, so that we can go and settle in Mars in coming future. So with that objective, US and Russia has done a lot of space explorations by using robots with the support of spacecraft. So I am going to show you small video clips where you can able to see how Curiosity land rover is put into a Mars with the support of spacecraft. There is a lot of things the scientists have considered. Most important thing is landing of rover, Curiosity rover. It's very, very difficult. Why? Because the spacecraft will take the Curiosity rover with a velocity of 13,000 miles per hour, and it has to land at zero speed. You just think it about. From the Earth to Mars planet, it takes minimum 8 months of travel. Later, it has to land very safely so that the robot can be utilized for exploring the space that is Mars, to find any organics or any minerals for our mankind in coming future. So let us see a small video clips now. See, this is the video clips. The spacecraft is taking the rover to the Mars. As I told you before, it takes 8 months, that is 256 days, to travel from Earth to Mars planet. Finally, landing is very crucial, and it is very important. It has to land at the required place where it is fixed. See, the Curiosity rover is hanging with the steel rope with the support of parachute. Can you able to see the balloon? Inside the balloon it is there. So it is with some velocity, it was impacted on the ground, and after some time it will get settled down. So once it gets settled down, already the program is controlled by the scientists at Space Research Station. They are controlling everything. Now you can able to see the rover which is inside the balloon. It is in safe. Yes. You can able to see the solar panels. It takes energy from the solar panels and performs various scientific operations. Operations like mining, testing, drilling. It will take n number of samples. This Curiosity rover has all scientific instruments fitted in itself. So it do all its research there itself, and it will give you only the sample of data through satellite, so that it can be used for further research. Yes. Now see the rover, Mars rover is going to land on the Mars. Similarly, you had seen the same thing. This is the Curiosity land roving.
Hello, I'm Hank Green, and welcome to this special edition of SciShow News. 8 months ago, the final stage of the Mars Science Laboratory's launch vehicle pushed the craft to 13,000 miles per hour, ready for its journey to Mars. The Mars Science Laboratory, or Curiosity rover, is a massive interplanetary payload, the largest ever delivered to the surface of a planet, and 5 times larger than any previous rover. The logistics of getting it not just to the surface of Mars, but to a very particular spot on the surface of Mars, boggle my mind. The calm of the first 8.5 months of this journey will end as the spacecraft enters the Martian atmosphere, still traveling at around 13,000 miles per hour. At that moment, the craft will lose contact with us. 7 minutes later, it will be going 0 miles per hour, either sitting peacefully on the surface of the planet, ready to begin its mission, or scattered across the landscape with no sign as to what went wrong. NASA scientists and engineers call this the 7 minutes of terror. As the craft enters the upper atmosphere and jets align it to the perfect entry vector, the friction of the atmosphere heats the heat shield up to 1600 degrees Celsius while slowing the craft down to a much more manageable 1,000 miles per hour. Still, though, faster than the speed of sound. But while the Martian atmosphere is certainly thick enough to burn up an improperly shielded spacecraft, it is not thick enough to slow it down to subsonic speeds. So that job is done by a parachute. The largest supersonic parachute ever designed, in fact, weighing only 100 pounds and yet capable of withstanding 6,500 pounds of force. But now, I have for you some more scary news. Because the Martian atmosphere is so thin, the parachute isn't enough to achieve a safe landing speed, so, you guessed it, a third stage is necessary: the powered descent. The parachute detaches and the falling craft is caught by retro-rockets which slow it further, jetting it away from the parachute so it doesn't get tangled up, and eliminating not just vertical but horizontal speed. The craft now uses radar and cameras not just to see how high it is, but to spot its landing area, so that it can hit the surface in a previously defined area that isn't just safe, it's also scientifically fascinating, at the base of a 6-kilometer high mountain. However, there remains one final problem. If it lowered itself all the way to the surface on rockets, the amount of dust kicked up in that process could permanently damage many of the instruments. So instead, the lander is lowered down on a 21-foot tether, a system engineers call the sky crane maneuver. After the wheels hit the ground, the rocket portion detaches, accelerates up, and then crashes at a safe distance. At this point, and only if all of those things go perfectly, the craft will send out a signal letting us know that it is safely on the planet's surface. And we can all let out a huge sigh of relief. I will be watching and live tweeting the night of August 5th, 1:30 a.m. Eastern, 10:30 p.m. Pacific. Please join me for one of the most intense scientific moments in human history. Thank you for watching SciShow News.
Okay. Now you have seen two small video clippings. In the first two clippings, you had seen the balloons is used for landing. Whereas in the second clippings, you had seen the steel ropes is attached to the Curiosity rover for the landing purpose. The balloon is used when the weight of the vehicle is going to be very less, small. Whereas if it is going to be the Curiosity rover vehicle is going to be very high, very huge, you have to go with strings, that is steel strings. So that is the difference between these two videos. Okay, coming to the next. You might have a lot of thinking. Let's see what you used to think one by one. What you're thinking, I have some videos related to this landing of Curiosity at Mars planet. Many of you may think like this: how do you get into Mars? That is Mars planet from Earth. We have answer for this. How do you choose landing site in Mars for landing of your vehicle? The next one, how do you land on Mars? Is it a very easy task? No. It's very tedious job. Lot of research has been taken place to land the vehicle on the Mars. How hard is to land Curiosity on Mars? Everything you can able to, we have answer one by one. How do rover drive on Mars? So you have put the Curiosity rover on the Mars. How it drives? Is there any driver? It is autonomous. Is it autonomous? No. Who is controlling? Scientists from NASA in the space station, they are controlling it. Okay. Next question, why is curiosity looking for organics? What is the need? So we will see all this, we will see answer to all these questions one by one. Let's see the first one. How do you get into a Mars?
How do you get to Mars? If you want to send a spacecraft all the way to Mars, first you'll need a fast rocket to escape the pull of Earth's gravity. The heavier your spacecraft, the more powerful your rocket needs to be to lift off. Next, make sure you launch at the right time. Mars and Earth orbit the Sun at different speeds and distances. Sometimes they're really far apart, and other times they come closer together. About every 2 years, the two planets are in perfect positions to get to Mars with the least amount of rocket fuel. That's important. The total trip is over 300 million miles. Finally, make sure your aim is right. You can't shoot for where Mars is at launch time. You have to aim for where it will be when you get there. It's a lot like how a quarterback passes a football. Also, you may need a few thrusts to correct your direction along the way so you don't miss Mars. If all goes well, you'll get to the red planet in about 7 or 8 months. Then, if you actually want to land on Mars, well, that's a whole other challenge.
Hope you got some answer. How to get into Mars. Let us move on to the next one. How do you choose landing site in Mars? Where to land? Can we able to land in any place in the Mars by putting worth of money like billion dollars for exploring the Mars? So we should choose the landing site. That is very important. You get the answer from here.
How do you choose a landing site? So you want to study Mars with a lander or rover, but where exactly do you send it? It's a tricky question for engineers and scientists. You want it all, to land, work, and discover. To land safely means no high elevation sites where there isn't enough atmosphere to slow you down in time. And try to avoid places with steep slopes or big rocks that could damage something. You also don't want to sink into a thick layer of dust. Working is easier near the equator, where seasons aren't so extreme and where solar panels can get lots of sun. And of course, don't send a rover somewhere it can't drive. Most important is what you want to discover. Some sites are great for studying rock layers, others might be perfect to listen for quakes. Using Mars orbiters, you can collect lots of data on potential sites. When you find the best spot to land, work, and discover, you've found your new home on Mars.
Hope you got answer for how do you choose landing site in Mars. Okay, we will go to the next. How do you land on Mars? You find a site, landing your vehicle. How do you go there? You can send a Curiosity vehicle through space, but landing is very crucial. If you don't land, if any instrument get damaged, whatever you had invested for long time, it is going to be waste. So you see that how do you land on Mars? The answer is here.
How do you land on Mars? Very carefully. Your spacecraft hurtles toward the planet at thousands of miles per hour, so you'll have to hit the brakes in a hurry. First, your capsule needs a heat shield. It protects the spacecraft inside from the heat and friction of entry into the atmosphere. Friction slows you down over 90%, but not enough to land safely. Use a parachute to slow down even more. Still, falling at over 100 miles per hour, you need the right system to land safely. Here are some options. With a small to mid-size rover, use a cushion of airbags along with retro rockets. Impact at 30 miles an hour and bounce to a stop. With a large lander, use retro rockets and landing legs to touch down going about 6 miles an hour. Or with a large heavy rover, use a big jetpack to slow down to under 2 miles an hour. Then gently lower it on cables to land on its wheels. Any way you do it, you'll need skill and hard work. There's nothing easy about landing on Mars.
You got the answer how to land on the Mars? It's not easy, but the NASA has did it. That is the research work they have done with the robotics. Next, we'll move on to the next question. How hard is to land Curiosity in the Mars? We will have the answer. Just see this clips, video clips.
How hard is it to land Curiosity on Mars? On a scale from 1 to 10, landing on Mars is a 20. Curiosity is the biggest, most capable Mars rover yet, and needs a new type of landing to reach the ground safely. In this 7-minute trip to the surface of Mars, we have to slow down from over 13,000 miles an hour down to 0. Hundreds of things have to go just right. Curiosity must hit the atmosphere at just the right angle, endure extreme heat from friction as it descends through the atmosphere, open its parachute at just the right time, use radar to know exactly how high it is, free itself from the parachute, perfectly fire 8 rocket engines to slow final descent, drop down dangling on 4 cables, lock its wheels into place just before landing, and cut the cables right at the moment of touchdown. And even if we do everything right, Mars can always surprise us. It's a big challenge, but a big opportunity to help unlock the mysteries of Mars.
Go see how hard to land Curiosity in Mars. The NASA has did it. We'll move on to the next one. How do rover drive on the Mars? Rover, that is the Curiosity, that is robotic vehicle. How do it drives on the Mars? There is no driver. It is not automatic. It is controlled through satellites. Yes, this is what Industry 4.0. We are going to bring it in all the countries. See the small clips.
How do rovers drive on Mars? First of all, there's no joystick for driving a Mars rover. Before a rover hits the road, engineers send computer commands overnight, telling it where to go the next day. Depending on how tricky the terrain is, rover drivers have 2 options. They can send a string of specific commands like drive forward 5 meters, then turn right 90 degrees. The rover turns its wheels enough times to add up to 5 meters, and then turns in place. Or if it looks safe, they can let the rover think on its own. They write commands like, see that rock over there? Find your way there safely. Then, using 2 cameras like human eyes, the rover gets a 3D view of hazards such as large rocks and steep slopes. After mapping the danger zones, it plots the safest route to avoid them. Either way, did the rover complete its drive as planned? Engineers double-check when the rover sends back a postcard of its new spot on Mars.
Got how the rover drives on the Mars? We will move on to the next one. Okay. What is the purpose of taking the Curiosity vehicle, that is robo vehicle, to the Mars? What is the purpose? We want to see the organics in the Mars. Is there any organism which is living in the Mars? If we found, then it's good. Human being can go and live in the Mars. Let's see. These clips, you will come to get the answer.
Why is Curiosity looking for organics? Organics are carbon-based molecules, key ingredients to life. If Curiosity finds organics in ancient rocks, there's a better chance Mars once had good conditions for small life forms called microbes. But finding organics is hard. That's because organics easily break down when exposed to harsh things like extreme radiation and chemical oxidants that gave the Martian surface its rusty color. A great place to look for ancient organics today is in rock layers. Organics that were quickly trapped and buried in layers of mud or in sediments that sank to the bottom of a body of water could have an especially good chance of being preserved. Scientists think Curiosity's landing site, Gale Crater, contains those special layers, created in ancient times when water was present. The water dried up long ago, but rock layers that remain today could still preserve organics inside. If Curiosity finds organics, it wouldn't prove life existed, but it sure would improve the odds that Mars once had the right ingredients for life.
Now you got the answer. Why curiosity is looking for organics in Mars planet? Yes, right. Okay. Coming to the introduction slides. So we have covered a few video clips. Interesting one, how space explorations was taken place with the support of robots. Yes. We will move on to the next one, Earth-based robots. That is, in the planet of Earth, what is going on? Let's see. Yes. Planet, that is the robots on the Earth planet. See, this is the rover which is designed by Tokyo Institute of Technology, Japan. It's a planetary rover with transformable beam. This is the academic projects done by many professors and students. Let's see how the technology has grown in robotics when it comes to Earth, robots on Earth. See here, the robot is picking and placing. It is used as pick and place robot here. And the child robot is again going to the mother robot to perform its task with the mother robot. Got it? See, this is the technology which we need to develop to put our India on the Mars. It's all with our students and professors. If we think we can able to do it, it's all time bound. When there is a will, there is a way. Okay, we will move on to the next robot. The next one is biological inspiration robots. What does it mean? It means that this biological inspiration robots, which is used for spying purpose, it is for defense. These robots are mostly utilized for defense purpose. Just to see how the technology has grown. Insect robots, the small mobile insect robots.
This video describes a new biologically inspired robot series called Mini-Wigs. These 9-centimeter long robots can run at sustained speeds of over 10 body lengths per second and navigate challenging terrain. They are more compact versions of our larger WIG series of robots, which benefit from abstracted biological principles derived from cockroach locomotion. Cockroaches normally walk and run in an alternating tripod gait. In normal walking, they swing their legs high and in front of their bodies so that they can climb smaller obstacles without changing their gait. The previous WEGS vehicle uses one large drive motor to propel its 6 appendages in a nominal alternating tripod gait. Its 3-spoked appendages, called WEGS, combine the speed and simplicity of wheels with the climbing mobility of legs. Its 6 axles are compliant so that its gait passively adapts to the terrain and it can climb larger obstacles with its contralateral legs in phase. To be more compact, Mini WEGS uses 4 WEGS that move in an alternating diagonal gait. Like the larger WEGS vehicles, it is battery powered and radio controlled, and it uses only one motor to drive all of its WEGS. It also uses one microservo for steering its front WEGS via a rack and pinion mechanism. The robot is highly mobile, maneuverable, and versatile. It can surmount obstacles greater than the radius of the WEGS, a difficult feat for wheeled vehicles. It can run forward and backward, upside down and right side up, and has a turning radius of 2.5 body lengths. On both smooth and rough terrains, it can sustain a high rate of speed of about 10 body lengths per second. Additionally, its robust construction allows it to sustain repeated falls from a height of over 10 body lengths and tumble down a flight of stairs with no damage. Some insects have other modes of locomotion to augment their walking ability. The cricket and click beetle, for example, can jump to surmount obstacles of immense relative size. Jumping Mini WEGS has been developed based on this concept. It can surmount obstacles 2 to 3 body lengths high, such as a stair. As the robot runs, the single drive motor simultaneously stores energy in a spring for jumping. After release, the mechanism is automatically retracted as energy is stored for the next jump. Deployment methods such as passive glider drops are under consideration. The robot survives a 7-story drop onto concrete with the aid of simple wooden wings. Note the power of the robot. It can carry the bulky payload of the wings and tail. In conclusion, Mini WEGS is an extremely mobile robot. Based on abstracted biological principles and building on the original larger WEGS vehicle, this small robot combines simplicity, robustness, and reliability to provide a desirable combination of speed, mobility, and versatility.
Got?
Yeah. Oh, stop it, stop it.
I am.
Wow. Got it? How the robots are created with the principles of biological inspirations. It's a small mobile robot which doesn't cost much to build, but the technology is very important to build. Okay, we will move on to next, industrial applications. In many industrial applications, robots are used for automation purpose. For example, in Chennai, every minute one car is get produced. This is a sample I am giving you. Every minute in Chennai one car is produced. For an hour 60 cars. You think about in a day 60 into 24. See, that much of car is produced only in the city of Tamil Nadu. How it is produced? Is it by using the human? No. It is used by the human technology, application of human technology in robots. It is called industrial robots. Here you can able to see the KUKA robot is a very famous robot which is used for industrial applications of automations in car manufacturing units. The example here is Tesla electric car manufacturing units. Just see this video clips. Most impressive robot. See the robot, how it is picking. One robo It is pricking the whole car and placing to the next side. It's a very coolest robo. See, Kuka robo, funnel. It's industrial robo which is used for automation purpose for assembly transmission line. That is the reason we could be able to produce, for example, one car in a 1 minute. That is the production it is taking place in Chennai, automotive city. We will move on to the next generation. Yes. How the robots it's going to be in applications in the next generation. Just see. This video clips will give you the understanding of robots for various applications in the coming generation.
You are watching Cold Fusion TV.
Hi, welcome to another Cold Fusion video. In the last robotics episode, we took a look at the most realistic robots in terms of strictly interaction or movement. Now we're going to take a look at the juicy stuff. In this video, we'll check out the cutting edge of 3 categories: robotic dexterity, versatility, and overall innovation. Let's begin with dexterity.
Dexterity.
When it comes to robotic dexterity and athleticism, there's no one doing it better than Boston Dynamics. The company, now owned by the Japanese firm SoftBank, was founded in 1992 and has since risen to become the leader in robotics. Atlas is a 6-foot humanoid robot that's been designed for search and rescue. Its abilities include navigating outdoor rough terrain and manipulating its environment. In order to see, Atlas is equipped with stereo cameras and a laser rangefinder. The robot is so advanced that it can now do some tasks that I'd say most humans couldn't. This includes successful backflips. When released in 2013, Atlas was an absolute breakthrough in humanoid robotics, as it could easily walk on uneven surfaces and even snow-covered terrain, and it can get up when knocked over. This is something that the previous generation of humanoid robots couldn't manage. Maybe to put some minds at ease, the Department of Defense has stated that it has no interest in using this robot for offensive or defensive warfare. Spot Mini. The canine-inspired Spot Mini weighs about 25 kilograms or 55 pounds and is much lighter than other Boston Dynamics robots. It runs off electricity and can operate for about 1.5 hours. Spot Mini is also the quietest robot from Boston Dynamics. In February 2018, a video of Spot Mini opening a door with a claw made it to #1 on YouTube trending, and a lot of people did find it a bit creepy, especially if they were a fan of Black Mirror. But I really just see good mechatronics engineering. So most of the footage that you've seen of Spot Mini is when the robot is in autonomous mode. But what some people might not know is that Spot Mini can actually be controlled by a human. Here's a pretty cool example of a TED Talk where that happens.
So this is Seth Davis, who's my robot wrangler today, and he's giving Spot some general direction by steering it around, but all the coordination of the legs and the sensors is done by the robot's computers on board. It's got a solid-state gyro and IMU on board. It loves to use its dynamic gates, like running. And it's got one more. Some of you may see that as a head and a neck, but believe me, it's an arm. And Seth is driving it around. Now he's actually driving the hand, and the body is following. So the two are coordinated in the way I was talking about before, the way people can do that. And in fact, one of the cool things that Spot can do, we call chicken head mode, and it keeps its head in one place in space and it moves its body all around. There's a variation of this that's called twerking. So Spot, I'm feeling a little thirsty. Could you get me a soda?
See,
Now for this demo, Seth is not doing any driving. We have a LiDAR on the back of the robot, and it's using these props we put on the stage to localize itself. It's gone over to that location. Now it's using a camera that's in its hand to find the cup, picks it up, and again, Seth's not driving. So we've planned out a path for it to go. It looked like it was going off the path. And now Seth's going to take over control again because I'm a little bit chicken about having it do this by itself. Thank you, Spot. Feel about having just finished your TED performance?
It was sleeping. It was sleeping.
Me too. Thank you all, and thanks to the team at Boston Dynamics who did all the hard work behind this.
Another robot that Boston Dynamics has is Handle. Handle combines the dexterity of other Boston Dynamics robots, but with wheels. It stands 6.5 feet high and can travel about 15 kilometers an hour or 9 miles an hour. It also runs on battery and can travel a pretty impressive 24 kilometers or 15 miles on one charge. And to add to this, it can jump 4 feet high. Versatility. Honda's Asimo robot takes the cake for the most versatile robot in terms of ease of integration into various target markets. Asimo, which stands for Advanced Step in Innovative Mobility, has the ability to make sense of its environment via facial and sound recognition, but this goes a step further. Asimo can also understand postures and gestures such as handshakes, pointing or waving. This enables the robot to interact with humans quite well. It's also capable of detecting the movement of multiple objects, including distance and direction. This is achieved by 2 cameras in Asimo's head, acting as its eyes. Asimo can follow a face or turn its head to a person when being approached or spoken to. The robot also has the ability to recognize general sounds, such as an object falling or other loud noises. Overall, the robot is very multifunctional and can perform a number of general tasks, such as turning on light switches, opening doors, carrying objects, and pushing carts. Now, let's take a look at innovation. This one comes from the field of medicine. It's the Da Vinci robot, and I think it's a pretty good idea. The Da Vinci system is robotic technology that allows a surgeon's hand movements to be translated into smaller, more precise movements, using tiny instruments inside of the patient's body. The Da Vinci has 2 parts: a tower where the robotic arm operates, and a separate console where it's being controlled by the surgeon. The tower is positioned directly over the patient during surgery and is equipped with 4 controlled computer arms. 3 of them have a wealth of surgical instruments, and the 4th is equipped with 3D cameras. At the console booth, the surgeon can operate the controls while looking through a stereoscopic monitor. This monitor provides an HD 3D view of the area being operated on. The end result is now hyper-precise movement without human artifacts such as shaking. Here's an example of the system performing a mock surgery on a grape. In the medical field, the Da Vinci is currently used for cardiac surgery, general surgery, head and neck surgery, urologic surgery, and various other surgeries. So finer and more controlled movements surely have their advantages, but some critics note that the Da Vinci system ultimately limits the creative freedom because the software can't be altered by physicians. So let's move from the operating table to somewhere completely different. Deep sea exploration. And we'll start off by Stanford's Ocean One robot. This robot is pretty interesting. It's a humanoid android that stands in between a human diver and an autonomous underwater vehicle. Stanford's Ocean One robot is supposed to dive into areas that are too dangerous for humans and likely to be damaged by traditional autonomous vehicles, areas such as coral reefs. Ocean One is controlled by a human who receives haptic feedback on the controls when the robot touches something. So the next robot takes this idea a little bit further. It's a fish robot called SOFI. In general, we as humans know next to nothing about the vast oceans on this planet and the life that lives within it. For example, the very first footage of the elusive Greenland shark, which can live for more than 400 years, was only captured in 2011. One solution is to have a robot that actually looks like a convincing part of wildlife, so it can swim close to and study ocean ecosystems without being detected. MIT researchers have recently just successfully tested SOFI in deep diving, and it can swim up to 40 minutes at once. It easily handled currents and took high-resolution photos and videos using a fisheye lens, somewhat ironically. Robert Katzmann is head of this research at MIT's Computer and Science Artificial Intelligence Laboratory, and he says, quote, "To our knowledge, this is the first robotic fish that can swim underneath in 3 dimensions for extended periods of time. We are excited about the possibility of being able to use a system like this to get closer to marine life than humans could ever get on their own." End quote. The scientists hope that SOFI can shed some light on the ocean's deep mysteries. Staying on the topic of animals, our next robot is a cat. OpenCat is an interesting approach to robotics. It's a low-budget, yet capable, simple kit project for those wanting to learn about robotics. Inventor Rongzong Li explains, quote, "We are developing programmable and highly maneuverable quadruped robots for STEM education and AI-enhanced services. Its compact and bionic design makes it the only affordable consumer robot that mimics various mammal behaviors and reacts to its surroundings. Its innovative soft joints reduce wear or shock and extends the lifetime of hardware." End quote. There are 2 versions, one that uses an Arduino motion module for real-time adaptation, and a full version which uses a Raspberry Pi to enable AI-enhanced perception. The Pi brings Wi-Fi, Bluetooth, and touch distance sensors, voice, and night vision capabilities. The project is geared at the less tech-inclined who still want to have some fun and something to play with. Lee states that the end goal would be like a little robotic cat Alexa or Android phone with an app store that you can download third-party applications and functions for. He hopes the end price will be about the same as the average smartphone. Okay, so this last one may not be a perfect fit, but I thought I'd chuck it in. These are robots whose sole purpose are to create as much damage as possible. And no, I'm not going to be revealing a secret rise of Terminator. What I'm talking about is those backyard-built robots from BattleBots in America and Robot Wars in the UK. When I was about 7 or 8 years old, I used to adore Robot Wars. In fact, I've told you guys before that the name of this channel was based on my old high school band's name, but even before that, Cold Fusion was the name of a robot I built in primary school. Anyhow, I had a look at the new American version of BattleBots and it's come so far. It's almost like a sport in ways, with different strategies and excited commentators. As you can see, there's some insane effort put into some of these machines. But as far as pure destruction goes, the title for this category has to go to Tombstone in the American series.
Bombshell needs the perfect shot, but Tombstone will not make that easy. Oh, one of the wheels has come off the bombshell already. Tombstone, line it up. Here it comes. Oh, annihilation for Tombstone at last. That's the exclamation point, Kenny.
So with that, we've come to the end of the video. So which robot was your favorite and why? So to recap, we have the efforts from Boston Dynamics with almost human-like balance and agility, the friendly robot from Honda, Asimo, the surgical Da Vinci robot that increases the technical abilities of surgeons, Ocean One, an android diver, SOFI, a swimming fish robot, OpenCat, aiming to bring robotics to everyone, and lastly, backyard-built fighting robots. Let me know in the comment section below. So I want to thank you guys for watching the whole way through this video. If you're new here, feel free to subscribe. This has been Dagogo, you've been watching Cold Fusion, and I'll catch you again soon for the next video. Cheers guys, have a good one.
Yes. How was this? These are the next generation robots, which is going to be for our mankind, for many applications. With this interesting video clips, we will move on to lot of mathematical and theoretical understanding how to design the robots. We will move on to the slides now. Yes. Now, hope you know robot now. What is the definition of robot? Robot is in 6 words, it's work. Robota, slave word. Menial or slave labor, forced labor. Robot they used as a slave. Robot got publicity from the play, that is from the movie Rosa Universal Robo during 1921 by Carl Cave. Until then, people have not think much about the robots. This movie made everyone to think robots. Hope our session of videos will think more about robots in your mind. In coming days, we all will design many robots to our needs, to the humanity. Let's see the next one. Next slide. International definition of robots. It's an automatically controllable, reprogrammable, multi-purpose manipulative machines with or without locomotion for use in industrial automation applications. This is the international definition for robot. The others, Japanese call the robot as rob or robe. The other terms for robot is reprogrammable machines or multi-purpose machine. Why? Because we can reprogram the robot to our requirement and it do n number of multi-purpose work. We call it as a multi-purpose machine. This is how the international people will call robot, robe or reprogrammable machine or multi-purpose machine. Then, when you design a robot, it should not harm human being at any cost. So, in 1940, Isaac Asimov has proposed 3 laws. Anyone has to keep this law and they have to design the robot. What is the first law? It says, a robot may not injure a human being to come to harm. What does it mean? Even though human being harm the robot should not harm the human being. Second law, the robot must obey the orders given by human being except when such orders would conflict the first laws. Got it? Robot must obey the order given by the human being except when such orders would conflict with the first law. Then, third law, a robot must protect its own existence as long as such as protection does not conflict with first and second law. So each law is depending on the previous law, first and second law. So finally, he had concluded the 0th law. Robot may not injure humanity or through inactions allow humanity to come harm. So what does it mean? Robot is a slave. We should use robots for our mankind, not for destroying purpose. Yes, robot should not destroy us. Okay? These are the 3 laws of robotics, very important laws by Isaac Asimov. Next, first commercial robots. First commercial robots has come out in 1962 by Unimation Incorporation. What does it mean? Commercial, anyone can buy the robots for their need and applications. So Unimation company founded the robo and he is the named as father of robots. And these robots have been installed in General Motor plants. See, this is the robo. We call this robo as a Puma robo. What does it mean, Puma? It's a programmable universal machine for assembly. P for programmable, U for universal, M for machine and A for assembly. So this is called programmable universal machine assembly robo, Puma robo, which was created by Unimation company and it was commercial purpose. Anyone can buy and they can install to the plant for their requirement. Next, coming to humanoid robots, we had seen the Asimov robots in the video clips, is it? This is used for to assist the humans for the daily needs. Okay, next, application of robots. Application of robots, it's mostly widely used in pick and place robots, space robots, military purpose robots, for inspection robots, and then industrial application in automations, for inspections, welding. Robots are widely used in hazardous places where human being cannot interact. These are some of the applications the robots can be used. Types of robots by application. Hard task robots, industrial robots, mobile robots, tele-robots. When the human being cannot do the repetitive work, in that place robot can be used. Military robots is called tele-robots. Social service robots, domestic or household robots, medical robots, school robots for entertainments, to learn. There is a tele-robots is also in space. Robot under the water, you had seen underwater vehicle which is connected with robot, and you have also seen the robot which is like a fish where it is used for the survey purpose to see what is inside the sea water. These robots are much useful to explore the sea to a depth of any height. So these robots are widely used in sea applications, surveillance applications. In military applications also, these robots will be used. Robots with other functions, robots in agriculture, beam robots. Even in agriculture, people are using robots for plugging and planting the seeds, something like that. And for watering purpose and for spraying the insecticides in the agriculture so that the cultivation can be, make it in a double or triple like that. So application of robots, wheeled robots for transportation purpose, and you can see that wheel and leg robots like what you have seen in JCB for plugging the ground sand, or for pick and place robots like that. Even snake-like robots, articulated robot mobile is available, parallel robots are available. So these are some of the applications of robots for certain applications according to the need. Now coming to the industrial robots, yes, we had seen the robots, we had seen what are the definitions, we had seen its applications. We should see the data. This is very important where India is now, so that we can contribute ourselves in robotic design. Coming to the applications, see, you can see a lot of applications like automotive, electrical and electronics, metal, automotive applications, electrical and electronics applications, metal and machinery applications, plastic and chemical products application, food industries and other applications. You can see that automotive applications has a huge market. Most of the robots are widely used in automotive sectors for lot of purpose like welding, spray painting, assembling operations like that. Coming to electrical and electronics robots, electronic applications, robots are used in assembly purpose, inspection purpose, metal and machineries where the temperature is getting involved, hazardous place, metal and metal industries, plastic and chemical where human being cannot intervene. These are applications where the robots can be used. Coming to the next statistics data, industrial robot populations, Asia, Australia, Europe and America. You just see that Europe, Asia and Australia, see all put together in Asia, see that the units which is 280,000 of units in 2017, and similarly it is in 2018, 19, in 2022 it will increase because of Industry 4.0. It is going to come and it is going to be existence in coming years. So industrial robots finds more application in industrial purpose. You see that the market requirement. America has a huge market for industrial robots, and next to is Asia, and next to is Europe markets. So anyone get into a design of robots, you have a good market to sell it. So keeping in this mind, young students, all young students of core engineering, even computer science and IT students can get into robotic design so that India can be more popular in robotics in coming days. Other robot populations, see here, service robots for professional use, main applications. See, this is the defense purpose. See, defense purpose is gradually increasing. For inspection purpose, gradually it is keeping on increasing. And logistic, nowadays logistic is very important because Amazon uses lot of robots for automating all the things. So these are the things, forecast. This is the forecast of service robots for professional use and for other applications. See that the huge market, public relationship, there is a huge market for the robots in coming days, coming years. So this is the data about the industrial robots need in the world. Okay, we will move on to the next slide. International Federation of Robotics data. So annual installation of industrial robots, this is the data of 15 largest market in 2018. See the China. China is a huge player. They install a lot of robots for mass production. Next to the China is Japanese. Then next to that is United States and Korea, Germany, Chinese, Italy. This is Taipei, Chinese Taipei, Italy, France, Mexico, Spain. Where do we? We stand very low. We use robots in industries at a very less number. Why? The awareness is not much. People are thinking it's a huge cost. Technology has not been transferred, and the cost is also adaptability of robo is it's very huge cost for Indian people. That is the reason they are thinking like that. Let's see what is happening in coming slides. Highest robot density in Singapore, lowest average in Asia. See the robot density manufacturing industries. Singapore is the highest, Korea, Germany. See that these are the countries. So we cannot, Indian manufacturing of robot is very, very, very less. I will tell you the problem why. The reason for poor utilization of robots. What is the main reason? Mainly due to unemployment. Is it? When we use robots, we will get unemployment. Just think about Japanese. Japanese in 1992, they have 350,000 robots, but have only 3% of unemployment. It doesn't mean that using of robots will make us unemployment. This is not the reason. What are the other reasons? Other reasons, lack of proper perspective. It is not, we have not given the proper guidance for the industries to use robots. Cheaper labor. The reason is cheaper labor. In India we have a cheaper labor, so we are not using it. Non-availability. Robots are non-available in the current market. High import cost and high investment. Importing cost is very high and investment cost is also very high. That is the only reasons for Indian industries to utilize the robots. More reason why we are not using. R&D support by the government is very less. For academic institute, DST and DIT is spending money on robots. Other institute has to come forward in supporting robotics projects to the academic institutions and even for the students community. Company involved in manufacturing is very less in India, and advanced research absorption in robotics is poor. People, that is students community and even faculty communities, are not absorbing the advanced capability of research in the robotics. That is one of the poor area. We are very lagging in this area. Question: should India use robot? Yes, we should use robot. Does India robots? Yes, modified way. If yes, how? Let's see in coming days what is going to happen. Robotics in India. To overcome robotics versus unemployment, do we like to work in front of furnace? See, think about this. Can we work at a 500 degrees C of hazardous place? It's very difficult. Weld 2 parts for 8 hours per day for several years. Repetitive work, very difficult. Robot equal to machine, robot not equal to human being. So we can apply in such areas where it is a hazardous and repetitive work in the industrial applications. Where and how? The robots can be used in hazardous environment like chemicals, steel plant, nuclear plants, and plants like which is very, what do you say, not good for the human being. In such plants, robots can be used. High precision application. If you need more precision, we have to use robots. If you want to export any goods to any country, you need a precision component, we have to use robots. How? How can we use indigenous design, develop as a customized design, make awareness, think it as a mission. We have to get inside to design the robots to our need and to export to the world market. It is the need of the hour. When to use a robot? Thumb rule. Is the task dirty, dull, dangerous, difficult? Will a human be jobless? Is a human willing to do a job, repetitive job? Is robot usage economic? So these are the questions we have to answer, and we have to think, and we have to use the robots. Then coming to robot subsystem, now we know what is robots. Any industrial robots will have these types of subsystems. See, it is like a human. It is the base, wrist, shoulder, this is the upper shoulder, and this is the this is the shoulder, and this is the lower arm, and this is your wrist. Clear? So robot parts are what? Base, it has a revolute joint, it is like a hip. So this is the upper arm, lower arm, and wrist. Got it? And robot subsystems, any robots should have vision, because vision is very important to make the robot as autonomous. You need sensors for this vision, and you need a computer, and you need a control systems to do the work very accurate and more precision. So this is the robot. See the whole robot, it is placed here. This we call it as a what? What robot it is called? Can you tell? This is called Puma robot, industrial robot for industrial applications. Clear? We'll move on to the next slide. Subsystem of industrial robots contains what? Manipulator. Manipulator is something like arms and wrist. End effector It is a very important thing in the robo. Once you buy a robo from the supplier, they will not give you the end effector. They will give you only this robo. This end effector, according to our application, we have to fix it. Okay, this is the end effector. Actuator in set motion. What is the actuator? How do you control it? The actuator may be hydraulic, may be electrical actuator or pneumatic actuator. Clear? Hydraulic actuator, it is used when you need to move heavy loads. Then you have to go for hydraulic actuators. Now you need more efficiency. You can use pneumatic actuator for lightweight pick and place robot. Electrical actuator are currently most widely used nowadays because to have a precision control, easily controllable. Maintenance is very less when compared to the hydraulic and pneumatic. So nowadays most of the robots are going with electrical actuator, where BLDC motors are highly used because of higher efficiency. Brushless DC motors. That is the technology that is going on in electrical actuators. Transmission, recognizations. For recognition you need sensors. That is, this is ADC, analog to digital control, and the control supervision like digital to analog control, digital controller, GPS. So robot is something like, it bring all the department together so that the robot will be more perfect. See here, the IT and computer science department is involved, electronics is getting involved, mechanical is getting involved, control system, electrical engineering is getting involved. So put together all the department it needs to get involved to design a proper robot according to the requirement. Next. Classification of robots. How do you classify the robots? Robots can be classified according to Cartesian coordinates. You can able to see this type of robots for drilling holes for inspection purpose, pick and place. In Cartesian coordinates, the robot moves only in 3 coordinates, that is X, Y and Z. It doesn't have any rotation, only the translation will take place, displacement will take place. That is called Cartesian. Cartesian coordinates, the movement will be linear, X, Y, Z directions. Okay, this is the example of Cartesian robots for drilling purpose. Cylindrical purpose, cylindrical robots. Cylindrical robots, it has a revolute joint. See that the joint is revolute joint. In cylindrical robot, this arm will revolve about this axis. If this is going to be the Z axis, it will revolve about the Z axis. Okay? This is called cylindrical robots. You have a cylindrical shape. In Cartesian, you have a rectangular shape of work volume. Next, coming to spherical robots. This is called spherical robots, where the robot can have a work volume in a spherical volume. 3D space. The robot end effector can trace concentric spheres in 3D space. Can you able to see 3D? This we call it as a spherical robot. You have 2 joints. The rotation about x-axis, the rotation about z-axis. So that, and there is a translation to move from here to here. We call this robot as a spherical robots. You can see the spherical robots. Next, coming to SCARA robots. This is a very important robots. Selective Compliance Articulated Robot Arm, SCARA. Okay. This we call it as RRP robot. Here you can able to see that there is a revolution about 3 axes. One axis here and other axis here and other axis here, and there is a translation movement from here to here. This we call it as a SCARA robot, selective compliance articulated robot. For tabletop assembly robot, for assembly purpose, it is used in industry for assembly purpose. Now articulated robot. Articulated robot resembles a human arm in the 3D motions. It is like human. Articulated robot, anthropomorphic, it is like a human robot. What human is doing, the same thing the robot will do. We call that robot as articulated robot or anthropomorphic robot. They have 3 revolute joints with 3 variables. This is, see here, it revolves around this axis. Can you able to see the axis, z axis? It revolves the θ1 z axis. And if you take this as a y axis, it revolves around y axis. And here it revolves around a y axis. So what is the degree of freedom for this robot? The degree of freedom is how many joints it has? It has 3 joints. 1, 2, 3. 3 degrees of freedom. It has 3 degrees of freedom. This is the classification of robots. So we had seen Cartesian robots, cylindrical robots, spherical robots, SCARA robot and articulated robot. Next. Now next, coming to the robotics for students, there are number of softwares available in the market. We had plotted a few diagrams which we have simulated in Adams. See, this is the Cartesian robots. We have modeled the model in Adams and we had simulated it. Rigid body dynamics. We call this a rigid body dynamics. Cartesian robot having Cartesian, that is 3-dimensional movement. Cylindrical robot which has only 1 rotations. And this is spherical robots. This is articulated robot, Puma robot. So students can use softwares like MSc Adams, and there is a software, it's a free software which you can able to download with no time. The IIT Delhi has come out with software. Professor S.K. Saha and his team has come up with software like robo analysis software where you can simulate it. It's very easy to learn. Tutorials are available inside the software. Just a small robot you can design and you can simulate it. You can see the experience of your learning. This is where you can do, students can work with virtual lab. No need to have a robot. You have a software, you have a laptop, model the robot, simulate it, see and get experience. Later you can do lot of projects in this. So students can get into projects of robo computations like mobile vehicle, like insect. We had seen a lot of insects like small mobile robot. We had seen robots like which is helping the human being, like a fish. We have seen the robot. So if you want to design, you can use the software and you can simulate it, the rigid body dynamics, using MSc software. In HyperWorks there is a software called Recordine. MSc Adams, this software is from MSc software. And ANSYS, it has multi-body dynamics. CATIA has its own multi-body dynamics. Creo has its own multi-body dynamics where you can perform all rigid body dynamic simulations. Okay, next. This is very, very important. If you want to design the robot, there is 2 kinematics is involved. One is called direct kinematics and another one is called inverse kinematics. This is the topic of interest which we are going to deal in coming days. In the next sections, we are going to deal about direct and inverse kinematics, that is forward kinematics or direct kinematics, inverse kinematics. What is about? See, you have the end effector here. These are the links and these are the joints. If you know the theta for given for the joints relation, rotation, translation for the robot arm, what is the orientation and position of the end effector? You can find out the position of the end effector by knowing what? That is theta and translation movement. You can able to position this end effector. This is called direct kinematics. What is inverse kinematics? Inverse kinematics, you will be knowing this end effector point. You want to find out the theta and the displacement. This is called inverse kinematics. So, knowing the end effector point in the space, finding out theta and translation distance d, that is called inverse kinematics. Knowing the theta and translation distance, you can able to find the end effector point. It is called direct or forward kinematic. This is what we are going to deal. It's purely about homogeneous matrix, transformation matrix, that we are going to design, that we are going to deal in the next session tomorrow. So the topic of interest is going to be direct and forward kinematics, inverse kinematics, and what do you mean by kinematics and dynamics? Kinematics deals about position, velocity, acceleration. In kinematics, no forces get involved, whereas in dynamics, forces get involved. That is called dynamics. Next to that is control. Then next is simulations. This is the topic of interest, and any engineer should know to design the robot to the requirement of any applications. This is the topic of interest. With this, I conclude my session. Thank you one and all. Thank you for watching. Any queries, you just text it. Tomorrow we will discuss it, and we will start to discuss about forward and reverse kinematics, that is homogeneous matrix, and one important thing is called DH parameters. DH parameters. So tomorrow sessions will be about forward kinematics, homogeneous matrix, and DH parameters. If you are learning, this is all about mathematics. It's all mathematics, simple mathematics. If you are good at matrix, that is sufficient. You can able to do a forward kinematics. We can able to find out the end effector point in the space in the tomorrow session. Thanking you one and all. Thanking you. I am very thankful for the opportunity which is given by Mahendra Institute of Technology, Professor Ganesan of Automobile Department, and I am very thankful to the principal of Mahendra Institute of Technology for giving the opportunity, and the management. I am very thankful to our management, Velammal Institute of Technology, for delivering this type of lecturers to the other institutes of students in Tamil Nadu. Thank you so much. Thank you one and all. Thank you for watching. Any queries you can. This is my mobile WhatsApp number and this is my mail ID. You can post your queries. We will answer tomorrow. Thank you one and all again. See you tomorrow.